Hello there, Mr. Sutton here, bringing you the Algebra 2 5.2 lesson on properties of rational exponents and radicals. And this is going to be a two-parter. It's kind of deceiving. The only objective we have is to simplify constant and variable expressions containing rational exponents and radicals. But this one little statement here, there's a lot going on in this lesson, so put on your seatbelt. Here we go. We're going to start this lesson off with a review of some important exponent properties. We're going to be doing a lot of work with radicals in this lesson, but as we saw in the last lesson, radicals basically are exponents or can be expressed that way. So the more we know about exponents, the better we'll deal with radicals. So what I'd like you to do is pause the video if you want and see how many of these exponent rules you can remember. Alright, so let's go through these one at a time, and they all have kind of a special name. So we have the product of powers here. So we've got basically the same base, and if we're multiplying these together, we're going to be adding the exponents. So this is a to the m plus n. And here we have the power of a power, something to a power raised to another power. In that case, we multiply the exponents, so a to the m times n. And here we have the power of a product. In this case, everything in the product can get the power. So we have a to the m times b to the m. We have a negative power, so that just gives us the reciprocal, and we saw that in the last lesson. We could rewrite this as 1 over a to the positive m power. And we're going to start putting some stipulations in here. In this situation, a can't be 0 because we don't want to divide by 0. Now this next one, the 0 power, anything to the 0 power except for 0 equals 1. So again, we're going to stipulate that we're not raising 0 to the 0 power. And then we have the quotient of powers. So this is kind of the reverse of the product of powers. Instead of adding the exponents, if we're dividing these bases, we're going to subtract the exponents. So this is a to the m minus n. And again, we don't want a to be 0. Now for this last one, we have power of a quotient. This is kind of like a power of a product, but with division, because multiplication really is division when you get down to it. So we can basically just distribute this exponent to the a and the b. So we have a to the m over b to the m, and this time around we want b to not be 0. It's okay if this numerator is 0, but not the denominator. Now one thing that's very important to know about all of these rules, I mean, we expressed the relationship is going one direction here, but all of these properties also work in reverse. For example, if I have two things being multiplied together and they both have the same exponent, I could multiply those two things together in a parentheses and have just the one exponent there. Same thing with division. And for example, if I had something to a power, I could unadd the exponents in that power and break it up with multiplication. So lots of ways to use these properties. Now that we've gone through some of those exponent rules, we're going to do a few examples. So there's nothing conceptually super new about what we're about to do in these problems right here. The main difference from before is that now our exponents have fractions in them, which just adds kind of another level of complexity because you have to remember how to do basic arithmetic with fractions. So with that in mind, pause the video and see if you can do this first example. Alright, since we have the same base and we're multiplying, that means we're going to be adding the exponents. So we're going to have 7 to the 1/4 plus 1/2 power. And we just need to get a common denominator and add these together. So this is really 1/4 plus 2/4. So that would be 7 to the 3/4. And they said that we can leave this in simplest exponential form, so this is fine as long as we don't have any negative exponents. Alright, so pause the video again and try out this second example. Now with this second example, we have the power of a product. That means that we can raise each of these terms individually to the second power. So we have 6 to the 1/2 to the second power, and we have 4 to the 1/3 to the second power. And remember that when we're doing that, we're multiplying the exponents together. So in this case, this is 6 to the 1/2 times 2, which is just 6 to the 1, or just simply 6. And here this is just going to be 4 to the 2/3. So we have 6 times 4 to the 2/3, and we can't really simplify that anymore. For this third example, we have some division of like bases going on here. Pause the video and give this one a shot. Now, since we're dividing the bases, we're actually going to be subtracting the exponents, and this 5 in the numerator has an invisible 1 for the exponent, so this is really going to be 5 to the 1 minus 1/3 power. Getting a common denominator, this is like having 3/3 minus 1/3, so this will be 5 to the 2/3. All right, try out this next one, and there's a few ways to do this next one that we'll go through, but give it a shot. So one way to do this one is you could raise each of these things individually to the negative 1/3 power and deal with it that way, and that's totally fine. One other little trick I want to show you though, if you didn't try it this way, since we've got the same exponent here, we could actually put the 42 and the 6 in a fraction in a parentheses and raise that whole thing to the 1/3 power, basically like undistribute the 1/3 power, like so. So we could call this 42 over 6, all of it to the 1/3. And the benefit of doing this is now I can just deal with these two exponents kind of individually instead of having multiple exponents. We can also do 42 divided by 6 and reduce that. That's just going to be 7. And 1/3 times negative 3 is going to be negative 1. So we have 7 to the negative 1. And negative exponent just means reciprocal, so this is just 1 over 7. Before we talk any more about simplifying radicals, let's talk about some definitions. So we're speaking the same language. A good one to start with is actually the word radical. What does that mean? That's basically just some kind of root. And these roots can have different indices. The index of a root just tells you the type of root it is. For example, a square root, cube root, fourth root, fifth root, kind of any sort of root you want. And the index is the little number that you might see next to the radical symbol, a little bit up and to the left of it. Square root doesn't have a number because it's the most common one, but if it did have a number, it would be 2. And then cube root is 3, and the rest of them are kind of self-explanatory. Now we also have a fancy word for the term that's inside the radical. We call that the radicand, the expression inside the radical. It's a lot of syllables, but it's less than all of this. And one more expression, one more term actually, that we're going to want to talk about when we're simplifying radicals is the idea of a perfect nth power. This is just an nth power of some integer. Now we're used to doing this with squares, perfect squares, like 1, 4, 9, 16, but we also have perfect cubes, like 1, 8, 27, what's the next one? 4 cubed is 64, so all of those. We also have perfect fifth powers, fourth powers, sixth powers, any that you might imagine. These are all just powers of some integer. It's important that it be a positive or negative whole number. Now, just as another example, 32 is considered a perfect fifth power because it's 2 to the fifth. So we're going to find later on that we're splitting things into these perfect nth powers times another number. But we'll get back to that in a moment. So we're going to be doing some simplifying, and when we talk about simplest radical form, that means 3 things, just to review from when you probably did this with just square roots. So first off, we can't have any perfect nth power factors in the radicand. And the n, whether it's third or fourth or fifth power, that's determined by the index. So for example, if you have a fifth root and the number inside it, the radicand, is the product of like 32 times something else, you'd have to split that up and fifth root the 32. Now we also have another rule. There's 2 more rules, both regarding fractions. So we can't have fractions inside in the radicand. We don't want the square root of a fraction. We also, if we do have a fraction, we can't have any radicals in the denominator. It's okay if there's a radical in the numerator, but the denominator, that's a big no-no. And all of these rules are really just based on a time when they didn't have calculators, so it just made the hand calculations a lot easier to have these rules, but we're kind of stuck with them, so we'll just keep rolling with them. Now, to implement all this radical form stuff, there's 2 important properties of radicals that will help us out. One is the product property, which says that if you have a radical with a product in it, you can split that up into 2 radicals, the same index, with each of the factors. So for example, if you had the square root of 30, you could break that into the square root of 5 times the square root of 6. Now this rule goes both ways. You can if you have two roots with the same index, you can multiply the stuff inside together and put it in one big root. So there's kind of a moving out and a moving in aspect to this rule. The quotient rule is the quotient property basically works the same way, but with division instead of multiplication. So we can split this up into the nth root of a over the nth root of b. And again, just like product rule, we can go backwards, and if we wanted to, we could turn this into one big fraction inside the radical. Now that we have that background on radicals, we're going to try a few problems involving simplifying these radicals. And all the stuff we're going to be doing is non-square root because you've already kind of done that in past years. So we're upping it an index or two. So one situation you might encounter is if you have radicals that are already split up by either multiplication or division. In situations like this, it's always worth it to try merging the radicands together to see if their products or quotients end up being perfect nth powers. So for example, 12 and 18, if I multiply that, is that a perfect cube? 80 divided by 5, is that a perfect fourth power? I'll let you decide. Pause the video and give this first one a shot. Alright, so I'm going to try merging these together. So I've got 12 times 18 inside one big cube root. And what is 12 times 18? Well, let me just run that on the calculator. And it comes out to 216. Interesting. Now I happen to know that 216 is a perfect cube. It's 6 cubed. And I mean, if you're using the calculator to calculate this, you could probably take the cube root on there as well. But this comes out then to exactly 6, which is kind of nice. Alright, pause the video again, try out this next one. Alright, so just like before, I'm going to try merging these and see if something good happens. So 80 divided by 5, I'm going to put that inside one big fourth root. And I happen to know that 80 divided by 5 is 16, so we have the fourth root of 16. Now 16 is itself a perfect fourth power. This is 2 to the fourth power. So the fourth root of 16 then is just 2. And we're all set with that. For these next couple of examples, we have a radical that is just one radical instead of two. So there's a couple different ways to deal with these, but a lot of them involve splitting things up. So if you have just a single radical like this cube root of 135, one thing you can try in this situation is to split it into a perfect nth power times another number. And then nth root the perfect power. So we've got the cube root of 135. Are there any perfect cubes that go into 135? Pause the video and see if you can apply this reasoning kind of like you broke up square roots and take it the rest of the way. Alright, so perfect cubes. Well, we've got 8. That probably doesn't go into 135 because it's even versus odd. How about 3 cubed, 27? If you're not sure, you can always check it on a calculator. So let me go to Desmos and let me try out 135 divided by 27. And that comes out to 5. So that actually works out very nicely. I will split this then into the cube root of 27 times the cube root of 5. And then just nth root, the perfect one there, cube root of 27 is 3. So this is just going to be 3 times the cube root of 5. And this is as simplified as it's going to get. Alright, so we'll start this next one together. This one's a little bit trickier. First, we notice that we have a fraction inside a radical, and we know that's a no-no. That breaks the second rule of simplest radical form. But we also know that we're allowed to split this up. So we can call this the fifth root of 7 over the fifth root of 8. So that's okay. But we do have another problem at this point, and that is we now have a radical, this fifth root of 8, in our denominator, which breaks the third rule of our simplest radical form. And this is usually going to happen when you're splitting things up like this. Now, 8 is not a perfect fifth power, but our goal here is going to be to multiply this fraction by a number over itself that turns this denominator into a perfect nth power. So that'll be my hint to you before you try this on your own. Multiply your denominator by what it needs to become a perfect nth power. And pause the video and see what you can do with that. Okay, so we've got 8, and we have fifth power is what we're looking at here. So what are some perfect fifth powers? Well, 2 to the fifth power is 32. Does 8 go into 32? It sure does, 4 times. So if I were to multiply this fraction by the fifth root of 4 over the fifth root of 4, that would give me a fifth root of 28 upstairs, which I don't really care so much about, but it would give me a fifth root of 32 downstairs. And that is the key here, because I can now turn around and take the fifth root of 32 to just get plain old 2 down there. And 2 is just fine to have in the denominator. So this would be our final simplified answer on this one. So at this point, if you're taking this lesson as the non-honors CP version of the course, then this is the end of part 1 for you. You can pause the video, do some practice on all this sort of stuff, and then come on back. If you're doing the honors, then we've got one more problem we're going to do together before ending your part 1. So if you're taking the honors version of this course, I'm going to show you one more little trick you can use. And this is a very helpful trick if your denominator has 2 terms, at least one of which is a radical. This works just fine if they're both radicals as well, but at least one of them is a radical. So in this situation, we would multiply the numerator and the denominator not by radical 3, but we would multiply by the conjugate of the denominator. Basically, if you have a plus b here, you would multiply by a minus b over here. That would allow you to use your a squared minus b squared shortcut, in effect squaring both of these things. So I'll let you pause the video and see where you can go with this guidance, and then we'll bring it back together. Okay, so the conjugate of my denominator is going to be 5 minus radical 3, and I have to multiply by that over itself. I'm really just multiplying by 1, which is always legal and doesn't change the value of anything. So if I do that, in my numerator, 1 times 5 minus radical 3 is just 5 minus radical 3, so that was pretty painless. In the denominator, we're going to square both things and put a minus between it. Again, we're using this a squared minus b squared conjugate shortcut. So 5 squared is 25. Radical 3 squared is just plain old 3, and we are subtracting that. So when the dust settles, we have 5 minus radical 3 over 22. Boom! So that is it for part 1 of the honors version of this course. Pause the video, do some practice that also includes a problem or 2 of this, and then come on back and we'll be adding some radicals together along with working with variables. Welcome back. Whether you're joining us from the CP or the honors version of the course, we're both starting in the same place here. So we're going to be adding some things together. Now, one thing that's really helpful to know when you're in these various situations is that terms that have the same base and exponent, like we have in example 9, or that have the same radicals, which we don't have in example 10, but we'll talk about that in a minute, those kinds of terms can be combined, just like terms when you have all the terms with x's or y's. So with that in mind, pause the video and try out example 9. It'll be a quick one. Alright, since these are both being multiplied by an 8 to the 1/5, we can basically just add these coefficients of 2 and 10 and keep everything else the same. So this is just going to be 12 times 8 to the 1/5 power. And that's it. Now this next example, we have the same index, which is important, but we don't have the same radicand. So to have like radicals, we need to have both the same index and radicand. So in situations like this, you may need to simplify the individual radicals first before you have like radicals that you can combine. With that in mind, pause the video and give example 10 a shot. Alright, so if we're trying to simplify these, the only one we could really simplify is this cube root of 54. Now 27, we've already seen that that's a perfect cube, and we know that 54 is twice that, so we can break this up into cube root of 27 times cube root of 2. And that minus cube root of 2 is still along for the ride. So this is going to be 3 times cube root of 2 minus 1 cube root of 2. Now that we have like radicals, we can just combine the coefficients. Basically just 3 minus 1 gives us 2 times the cube root of 2. At this point in the lesson, we are going to segue into working with variables. And just as a little refresher to help you with that process, here's this problem where you need to simplify this. So you probably know everything you already need in order to do this. We've just got some fractional exponents, so it kind of makes the cut for this lesson. Pause the video and see what you can remember with doing this kind of stuff. All right, so we're going to go through one sort of type of thing at a time. First, we have 14 divided by 2, which is going to be 7. And then we'll do the x's. We've got x divided by x to the 3/4. Again, we're going to subtract the exponents when we have the same base. So we have x to the 1 minus 3/4, which is x to the 1/4. Next up, we've got y to the 1/3, and there's no other y's at all, so that's going to stay the way it is. And then finally, this z to the negative 6, it's a negative, so that can come upstairs and become a positive. So this will be z to the positive 6. So now that we've done a little bit with variables, we're going to throw them into some radicals and see what happens. For this first one here, cube root of 64 times y to the 6th. One little hint to help you out here, especially with the part where you have to take the cube root of y to the 6th, is to remember sort of a rule we learned in the last lesson for converting between fractional exponents and radical form. So the rule goes something like this. If you have x to the p over r, that can be converted to the x to the p power with the r root. This is just a way of converting back and forth between these. Now in the last lesson, we converted from fractional form to radical form. Here it's more helpful to go the opposite direction, which basically means that when you take the r root of something to a power, you're essentially just dividing the power by the root. With that in mind, see if you can apply that to example 12. Give it a shot. So first step in example 12, kind of optional, but I think it's helpful, is we're going to break this into pieces here. So I have the cube root of 64 times the cube root of y to the 6th. Cube root of 64 is just going to be 4, because 4 cubed is 64. And for y to the 6th, using this formula here, we've got 6 divided by 3, so that's going to be y squared. For this next example, we've got the 4th root of x to the 4th over y to the 8th. So on this one, there's a little bit of trickiness that's going to be happening, but pause the video and see what you end up with, and then we'll bring it back together and fill in any gaps that we need to. All right, so hopefully you decided that this would be another good situation for splitting things up. So we're going to go x to the 4th root of x to the 4th over the 4th root of y to the 8th. So far just splitting things up because we don't want to have a fraction inside a radical. And at this point, let's see if we can actually just take the 4th power of these things. I mean, we could try multiplying by something over itself, but let's see if it'll fix itself first. So if we take the 4th root of x to the 4th, this would just be x to the 1st, right? Because we have 4 divided by 4. But I'm not going to write x to the 1st. I'm going to write absolute value of x to the 1st. And here's why. We're going to need an absolute value if something that was an even power becomes an odd power after simplifying. So this is going to become absolute value of x. Now, if something was an even power and it's still an even power after simplifying, like this y to the 8th is now going to be y to the 2nd, 8 divided by 4, then we don't need an absolute value. Now you might be wondering why the difference. Why do we need this absolute value in the first place? Well, when you simplify, you're basically giving us something that does the same thing, behaves the same way as the original function. This original function, when you plugged in negative x values, the even power here made them positive no matter what. But if you didn't have this absolute value here, plugging in negative x values to the simplified version would suddenly make things negative. So we have to force that to come out positive just like the original. Now in the original, negative y values would have been positive, but if you plug negative y values in here, it'll still be positive because it's an even exponent. So it's the odd exponent piece that forces the absolute value. This next example has a fair amount going on. Even at the very beginning with the instructions, it's a little bit weird. It says simplify, assume all variables are positive. Now the reason they're saying this is because we don't need the absolute value that we saw in that last problem. if the variables are assumed to be positive. Then we don't have to worry about plugging in negatives. So really they're just doing us a solid and giving us one less thing to worry about when we simplify this. Now the other thing that's going on here is you'll notice that if you were to take the fourth root of, for example, a to the 7th, 7 divided by 4, that doesn't come out evenly. So how are we going to put something like that in simplest radical form? So we're going to follow our pattern of breaking things into the biggest perfect power times something else. But in this case, for variables, perfect nth powers are going to have a power that's a multiple of the index. So in this case, perfect powers of 4 that have variables, it's going to be that variable to some multiple of 4. So that's how we're supposed to split things up here. So if that makes any sense to you, pause the video and try this one out, and then we'll bring it back together and see where we stand. All right, so I'm going to do this in a few steps. First, I'm going to split this into 4 pieces, one for each type of thing. So I have fourth root of 16, a to the 7th, b to the 11th, c to the 4th. They are all, each of them individually, going to get their very own fourth root, just so I can kind of isolate them and pick things apart. So going through here, I'm now going to either take the fourth root if I've already got a perfect fourth power, or I'll split it up into a perfect fourth power times something else. So for 16, that is already a perfect fourth power. This is 2 to the 4th. So fourth root of 16 is just 2. For a to the 7th, the biggest perfect power of 4 that's less than a to the 7th is a to the 4th. You just have to pick the biggest multiple of 4 that's less than the exponent. So I'm going to split this into the fourth root of a to the 4th times the fourth root of a to the 3rd. For this next one, biggest perfect fourth power that's less than b to the 11th is going to be b to the 8th, because 8 is the highest multiple of 4 that's less than 11. So I'll break this up into b to the 8th times b cubed. So notice the pattern here. The other piece that you're breaking things into should not have an exponent that's equal to or higher than the index, because then you could break it up further. And then let's look at this c to the 4th. Fourth root of that is just going to be c. Now this is one of those situations where you started with an even power and now it's odd. We would need absolute value if they hadn't mentioned this bit in the beginning about variables being positive. So going back now and cleaning things up a bit, we have a 2. Fourth root of a to the 4th is just going to be a. And I'm going to do fourth root of b to the 8th next, because that's going to end up outside the radical. So that's going to be b to the 2nd. And then this c is also along for the ride. And now the stuff that's going to stay in radicals I'll put together. So we have the fourth root of an a cubed and a b cubed moving in together. And that is fully simplified. So we'll do one more of these deals with variables. This one we have a radical in the denominator, so we know what that means. We can't let that stand. When you're multiplying this to get something that makes this a perfect n power, just remember what we talked about with variables and multiples of the index. So pause the video and try this one out. All right, so I've got a y to the 8th, and my index is 3. So the next multiple of 3 that's after 8 would be y to the 9th. If I could make this y to the 9th, then I could take the cube root and get something that's not a radical. How do I get this to be a y to the 9th? Well, I'm going to have to multiply it by the cube root of y to the 1st. I have to add 1 to get 9 there. So I'll do cube root of y over cube root of y. That'll give me x cube root of y in the numerator and cube root of y to the 9th in the denominator. Cube root of y to the 9th is just going to be y cubed. And there's nothing else we can really do, so that's fully simplified. So at this point, if you are doing the non-honors CP version of the course, this is the end of the lesson for you. Thanks for coming along on this journey. I'll see you next time. If you're doing the honors, then stay tuned. We got one more thing to go over. So for the extra honors sort of thing in this lesson, the big thing we're adding here is we're just going to combine that whole business about radicals with variables and adding and subtracting radicals. So just one more extra little piece of icing on the cake here. Pause the video and see what you can do with this first example. I'm calling it example 15, honors 1. All right, so because we have like radicals, we can just combine these together, add the like terms. So this is just going to be 5 plus 6, or 11 radical y. So not too bad there. Now we've got our final boss battle. Based on what you know about simplifying radicals and adding and subtracting radicals, pause the video and see how far you can get on this one. Alright, so the first thing I'm looking at is to see if I have like radicals. I don't. The index is the same, or else we'd be totally out of luck, but the stuff inside is not. We need to get a more reduced, simplified radicand. So what I'm going to do is simplify each of these individually. So taking a look at this first one here, it looks like I can split this up. So I'm going to have a 12, a cube root of 2, and then I could write the cube root of z to the 5th, but I can break that down a little bit because my exponent is higher than my index. So the biggest perfect cube less than z to the 5th is z cubed. So we're going to do cube root of z cubed times cube root of z squared. And now we'll come back to this mess in a little bit. Let's move over to this next term. So I'm going to have a minus z, and then this 54, I can break that up into the cube root of 27 times the cube root of 2. We've encountered 27 a few times now. And then z squared, we can't really break that down any further because the exponent is less than the index. So that's just going to be cube root of z squared. All right, going back through here, we have the 12. We have the cube root of z cubed, which is z, so 12z. We have a cube root of 2 and a cube root of z squared that can move in together to be a cube root of 2z squared. And now moving over to this next term, cube root of 27 was 3, so this is minus 3z. And then we have cube root of 2 and the z squared, just like we had over here. So that also gives us cube root of 2z squared. And now, after simplifying, it just so happens we lucked out and have the same radicand, same index, same everything. So we can just do, and also on the outside, we've got a 12z and a 3z. So these are like terms all the way through. So if we have 12 of these minus 3 of these, that's just going to be 9z cube root of 2z squared. At this point, I have a radical proposal that we end the lesson, quit while we're ahead. Till next time, Mr. Sutton signing off.